Welcome back to this lecture. In the last lecture we were introduced the second order linear equations. We have introduced the concept of Wronskian, and we also seen the solution space of homogeneous equation is 2 dimensional, which is in some sense a remarkable fact, but the only difficulty compared to your first order equations where the solution could be easily founded by a integral calculus problem. There is no general method to find the 2 independent solutions. So, if you have a procedure to find independent solution, or if anybody can prove that independent solutions, then the entire solutions space can be understood as a linear combination of 2 independent solutions. Since there are no recipe, I will begin with 2 methods to how to find the independent solutions. It is not very general method, and still we do not have a complete procedure. So, we will start with one easy method. It may not work all the time, it depends on particular problems you are dealing with. It might work or might not work. So, let me recall the equation, general equation, recall the general equation. That is nothing but L of y. For shorter notation we will put it, or you can also put L of y, y prime, y double prime, that is equal to y double prime plus pt y prime plus qt y equal to 0. This is the general equation which we are going to introduce. So, the idea is to look for a solution of the form, look for a solution of the form. This there is no reason why such a solution we can look for, but then for certain equations it will work out. We are not claiming u and v are solutions, you are looking for a solution in the product form u and v, and if you are fortunate enough we will be able to find a solution, find u and v by solving some other easy equations. So, do a computation to that one. So, you can do the computation. I will not do the entire computation, but y equal to u prime v plus u v prime, and then y double prime. You can compute y double prime. When you compute y double prime, you get u double prime v, then u prime v prime 2 times will come, 2 u prime v prime plus u v double prime. Substitute in the equation, let me call this equation to be 1. Substituting in 1, you get a bigger equation, you will give you a large equation. You can have to substitute all that, you will get u double prime v plus 2 u prime v prime plus u v double prime plus pt y prime, you substitute, you get u prime v plus u v prime plus qt u v equal to 0. That is what. So, the next step is to make the equation, choose u in such a way that you try to remove the v prime term from the equation. So, you put in such a way that summation of this equation, not this one, the v prime term, this one, this combined term v prime is absent. So, step choose u so that v prime term is absent, v prime term is absent. As I said, the idea is to look for get equations for u and v which are simpler. That is, if v prime term is absent, you want to choose this way 2 u prime V prime plus Pt u this V prime equal to 0. That gives an equation for u prime is equal to 2 u prime plus Pt u equal to 0. So, this is an easy equation. This is an easy equation for u prime. So, you solve for u, and that is easy. This is an easy part. Solving u for is an easy part because it is a first order equation. So, there is no difficulty absolutely, but the next result is that it is possible that because there is no V prime term, but then u is already determined. So, computing u double prime u etc. is already known to you, but then there are no V prime term. So, you will have an equation. It is possible that the equation for V is not always true. If it is always true, it is a equation for V is easy to solve. So, let us see an example. If you are lucky, you will be able to do that. So, let us see a simple example. Again y double prime plus 2 t y prime plus 1 plus t square y. There will be plenty of equations to solve equal to 0. So, what is Pt here? Pt is equal to 2t, Qt is equal to, you should also get familiarized with how to solve equations, that is important, 1 plus t square. So, what do you get it? If you solve for ut, you can write down the equation ut is equal to, you can write down the earlier equation. So, equation for ut is this one. So, this is what your equation, Pt is easy. So, you can write down the equation for u and you can solve it. So, let me not spend time here. So, let me write, this will imply your ut is nothing but e power minus t square by 2. Now, substitute, that is the easy part, substituting and computing. Let me avoid a computation here because one can do it easily. Computing, you can write down equation, you can actually see that will imply V prime will double prime will be 0. You see, so you have a equation. This happens for this particular equation. So, you are looking for a solution of the form y equal to uv, and this will give you V is equal to C1t plus C2 and a general, and that will imply your yt is of the form C1t plus C2 into e power minus t square by 2. So, you see, so you have your solution nicely in this case. So, many examples can be done that way. So, I will just show that example. Now, I will go to the next method. Method 2 is called the reduction of order. Method 2, order reduction. This method is quite good, but then you have to pay a price. The idea of this method, you need to know one solution. So, if you know one solution, it gives you a method, a systematic method to find the second independent solution. And also, so assume a solution y1 is known. So, this is the price you have to pay. So, still we do not have a, so this so if you are able to find one solution, this method will give you a systematic procedure by reducing the order to find the second independent solution. What will happen if y1 is a solution a constant multiple cannot be a constant multiple will also be a solution, but then the constant multiple of y 1 cannot be an independent solution. So, that is the first observation one has to make it, and no constant multiple of y 1 will give you a second solution. So, the possible way to find a second solution, instead of multiplying by a constant, you multiply by a function itself. So, look for a solution of the form, look for a solution of the form y 2 equal to C t y t, C 1 by 1 t. You see, because if you take C as a constant multiple, you are not going to get an independent solution. Any constant multiple will always be a solution, but if you want to have a solution y 2 which is independent of the solution y 1. So, now do the computation. So, you have to do a bit of computation, I will not do the computation. So, the exercise is just to do the computation, do the computation. What are the computation you have to use it to it? Find the y 1 prime, y 2 prime, y 2 double prime, and substitute in the equation, and substitute in L by 2. So, you want L by 2 to be a solution to your equation. So, you L by u 2. You also use the fact L y 1 equal to 0, because y 1 is already given to be a solution to your homogeneous equation. So, choose L y 1 equal to 0, then you want y to be a solution. So, use L y 2 equal to 0. If you do the computation, this will imply you will get an equation C prime of t y 1 is known to you, plus you get C prime of t into 2 y 1 prime plus p is a function of y 1 is equal to 0. So, this is known to you because y 1 is given to you, this y 1 is known to you, though it looks like a second order for C prime, since second prime for C, there is no C present here. So, you can write down this in principle C double prime of t by C prime of t is equal to minus 2 y 1 prime by y 1 minus p. You see. So, you have an equation, even though it looks like a second order equation, but if you put, so let me use the color, if you put V is equal to C prime, will imply V prime by V is equal to minus 2 y 1 prime minus y 1 minus p. You see. So, that will give you, you can solve it. If you put V, so solve for V first. So, that is why it is called an order reduction, method of reduction of order. So, you are actually solving a first order equation here, you see. So, you have a first order equation, solve for V, which you can write it as explicitly because y 1 is known to you. So, you can write for solve for V t, and but this implies once you get solve for V, that is nothing but C prime of t is equal to V. Again you are solving. So, you have a second equation to solve for C. So, you see, first you solve for V here using the first order equation, and then V is given to you, and you can just write C t, and C t is nothing but integral of V t dt. You see, and V can be obtained from here, which is a function of t, which can be solved for that, which will give you. So, that is a method of reduction. So, let me give you an example again to begin with, an example for you. So, you have an example, a simple example I am trying to give you, t y double prime plus t square y double prime t y prime minus y equal to 0. As I told you again, there is still it does not give how to determine the one solution, that you have to do by trial and error or looking at the equation. You may have some way of finding them. For example, here, so immediately looking at this equation properly, if I choose y equal to t, y prime will be 1 and this will get vanished, and since y equal to t, this will get vanished. So, this immediately gives you, this may not be easy. If that is easy, we have nothing more to do it here. So, y t equal to t is a solution. You see, immediately you can see that y t equal to t is a solution, and then how do you the order reduction? You look for another look for, so let me call it y 1 equal to, look for y 2 t is equal to c t t, look for y t c t t. So, how do you do that one? So, yeah, one more point I want to do here. So, we have determined a solution y 1 and y 2. You can actually show that this y 1 and y 2 are actually y 1 and y 2 are independent solutions. You can compute the Wronskian from here. All that you can see that you can compute the Wronskian of y 1 and y 2 and see that the Wronskian is not 0, and so can actually prove that the solutions y 1 and y 2 are independent. So, which you can do it as an exercise again. So, if you compute this y 2 prime and if you do the computation a bit here, do the computation here, you can actually see that c double prime by c prime is equal to probably minus 3 by t. You can do the computation. So, that implies finally you do the computation, first compute c prime, not compute, solve for c prime by reduction, solve for c prime, then solve for c 1, and if you do this a small exercise, you can actually get that your C t is, you can take C t or any constant multiple, you can see that C t is equal to 1 over t, you see. So, you will have another solution. So, the general solution can be written as a solution not C t, C t you will get it as 1 over t square, that will imply your y 2 t is of the form 1 over t. You can take constant, that does not matter for independent. So, you get solution. So, the other general solution is your C 1 t plus C 2 y t. So, you see a general solution. You expect this singularity, because if you look at this equation, this is actually a singular equation. So, the solution singular have the problem. So, if t not equal to 0 and if you are solving only on the positive side of t, you have no problem with the thing. As long as you have a singularity, you will expect such kind of singular problem to show some singular behavior, which we have seen already in the previous examples. Okay. So, we will go to the here you can see that t and 1 by t are independent solutions. It is the same situation in the earlier case also. For general, this is a very general method to solve that one. Now, we will go to a special class of equations where a general method is available to the find the independent solution. These are second order equations, second order linear, second order linear with constant coefficients. We will do that second order constant equations. So, how does a Ly look like now? Your Ly will be of the form, I can put a constant here, A not equal to 0. So, there is no singularity A y double prime plus B y plus C equal to 0. You want to see that one. Okay. So, yeah, solutions that one. So, here how do you proceed with that one? Again observe the equation C y P y prime plus C y equal to 0. So, look here is a factor, this again we are trying to get some idea from using this equation. A not equal to 0, A, B, C are constants now, constants. Since A not equal to 0, one can divide by A and you can write in the PQ form itself, that is a thing. So, there is absolutely no singularity, but let me put it A here, because this is the form you have already seen when you study the spring mass system, where A equal to m, B equal to c the damping coefficients and C equal to k your spring constant. Now, you have also recall what we have done in the beginning in the module 1 when we have studied the spring mass system. If time permits, maybe I will do a very little about it, recall what we have done there in the module 1. So, let us do it, this equation. The one observation is that if y prime is proportional to y, that is y prime is equal to some ky with for some constant k, for some constant k. That will immediately tell you y double prime is equal to k y prime, but y prime is k y. So, I can immediately write instead of k, we already used it for some spring constant in that example. So, I want to preserve that. So, I will use here r y prime, this is equal to r square y. What it shows that if y is proportional to y, y prime is proportional to y, y double prime is also proportional to y with the proportionality constant r square. So, they immediately shows that if y prime is proportional to y, y double prime is also proportional to y. So, if the y comes out. So, if you substitute, that immediately tells you that you get a r square plus b r plus c of y equal to 0. Definitely this is a constant, a r square plus b r plus c is a constant, and you want y, of course, if y is identically 0, this will satisfy, and y identically 0 is a solution to your homogeneous system. But what we are interested is a non-trivial solution. So, if we want to get a non-trivial solution, for a non-trivial solution, we need a r square plus b r plus c equal to 0, and this is called the characteristic equation. So, immediately if you are starting with the solution of the form. So, what we have thing is that you started with the solution of the not started with the solution of the form. If you are looking for a, assuming that y prime equal to alpha y, that is nothing but y prime is equal to r y. So, if y is a solution to this equation, y prime equal to r y, then r will satisfy this one. That is, if y satisfies y prime equal to r y, that will imply r should satisfy a r square plus b r plus c equal to 0. The character, that is why we study always the characteristic equation with constant coefficients. So, the moment this has a solution, a r square plus b r plus c equal to 0 is a solution, and then if you look for a solution to this form, that will be a solution to your second order equation. So, what are the solutions to this equation y prime equal to r? So, that is a reason. So, look for a solution of the form, look for a solution what you study of the form y equal to e power r t, you see. So, this is just to motivate, most of the time it is introduced that look for a solution of the form y equal to r t. This gives you some motivation why we are looking for this solution, and that immediately implies a r square plus b r plus c equal to 0. So, you look for a solution of this form, and of course, this has two roots. This gives you two roots r1 r2. Solve it. What are the roots you get it? R is equal to minus b plus or minus square root of b square minus 4ac by 2a, you see. So, this gives you different situations. So, the cases. So, you will start with a different case. Case 1 is the case which you are easier case for AC positive. This is the first case. In this case, two real distinct roots, that is very important. If it is not distinct, you do not get a two solution. Distinct roots, therefore, y1 equal to e power r1 t. What is r1? With a plus sign here, with a plus sign here, and y2 equal to e power r2 t with a minus sign here, you get that e power r2 t. So, r1 is with plus, r2 t equal to thing. So, you have r solutions, r solutions. Are they independent? Are they independent? Simple exercise for you. Are they independent? A simple exercise. Show. How do you show? We have a good method to show independent. Show W of y1 y2 is at t not equal to simple computation, because you know y1, you know y2, you compute y1 y2 prime minus y1 prime y2, you can see that it is 0 if r1 and r2 are distinct, two distinct roots r1 and r2, that is important, r1 r2 and r1 not equal to r2. It is just a computation for anybody can do it. So, there is absolutely no problem. So, you have, so what would be the general solution in this case? General solution y is equal to a e power r1 t plus b e power r2 t. See, so you have that. Now, case 2. Case 2, b square minus 4ac equal to 0. This is a double root. So, therefore, r is equal to minus b by a minus b by 2a is a double root. Therefore, y1 we get only one solution, double root does not give you two independent solution, e power rt is one solution. You see, the moment you get one solution, now you know the method of reduction of order to find a second solution. So, use, here is a simple again exercise for you. I do not have to worry about that, that is an easy thing, and it is also nice to do it, so that method of reduction can be learned properly. Find a second root find a second solution y2, second solution y2 using y2 of the form C1 Ct, solution Ct into e power RT. So, you have a solution Ct into e power RT using the method of reduction or using the method of order reduction. Very simple computation, absolutely no difficult. Use the fact it is a double root. The only thing that use R is a double root. You have to use this. What is the meaning of double root? That is means AR square plus BR plus C equal to 0. Since it is a double root, its derivative is also 0. So, you have this condition 2AR plus B is also equal to 0. So, to use this both the facts. So, use this fact and you get it again, we can get y2 of the form T e power RT. So, you can solve Ct to see that it is nothing but T. So, what is the general solution? General solution. So, again, so this T is not coming in a very arbitrary one, it comes as a second root. So, it will be general solution yt is equal to C1 plus. So, you have C1 into e power RT and C2 into this one. So, that is C1 C2 T, or let me use AB, so that you do not get confused with that C A plus BT e power RT. Okay. So, you have a nice thing. So, now we will go to the case 3 with complex root. Case 3 complex roots. What are the complex roots? Here b square minus 4ac is negative. So, you have two complex roots R1. So, what are the, let me get the thing, minus b, R is equal to minus b plus or minus square root of b square minus 4ac by 2a. So, it is a negative. So, you will have R1 is of the form something like alpha plus I beta, 2 complex root, R2 is equal to alpha minus I beta. So, what is alpha? Alpha is nothing but minus b by 2a, and beta is of the form square root of 4ac minus b square. So, this is the minus, we take it out by 2a. So, that will give you e power r1t, e power r2t are complex solutions. Complex solutions, but it is an easy factor to see that when you have complex solutions, it will immediately give you real and imaginary parts are all real solution, real and imaginary parts are real solutions. So, and that will immediately give you e power alpha t into cos beta t, e power alpha t sin beta t are two solutions. Just write down e power r1 t, you get it, these two things, e power alpha t and e power are two solutions. What about their independence? Are they independent? Yes, they are independent, the two solutions which are independent. How do you compute? The same trick, there is no problem, independent, a simple computation is not our real exercises, but it is a simple computation which one have to vary. So, if you compute, so this is your y 1 and this is your y 2 here. So, you will have you compute e power w of y 1 w of y 2. If you compute you will get nothing but you compute this, you get beta into e power 2 alpha t maybe. So, you will have a computation that is not a problem, because you can just compute y 1 y 2 prime and y 2 y 1 prime y 2, you get it. This is not equal to 0, why? Why? That is easy, because this is non-zero, which is exponential, and beta is non-zero, because beta is a we are in the situation of complex roots, since and b square minus 4ac is negative. So, this is non-zero, you see this is a non-zero commodity. So, if it is a complex roots, it is a complex roots, your beta should be non-zero, because beta equal to 0 is the case where you have real roots, you see. So, that proves immediately they are independent. So, this completely gives you the complete analysis of your equations with the constant coefficient. You can always determine if the equation with constant coefficients the two roots. With this thing, now we will go to the general case of non-homogeneous equation. And today first in the first lecture, in this lecture homogeneous equation, in this particular lecture we will give you the thing. So, what is a non-homogeneous equation? You have L of y, general case, it is not the what I am going to give you is about the general case, not necessarily with the constant coefficients. I want to understand the solution structure of this case. Ly is equal to y double prime, this is Ly by definition, plus Pty prime plus Qty is equal to some Rt. You already seen that using the existence uniqueness theory, an initial value problem has a unique solution. Under that is a proof which we already stated in the beginning. When P, Q and R are continuous, the initial value problem has a unique solution to the homogeneous equation. But the idea is to understand the solution structure. Naturally, you cannot expect a linear space now, because if you have two solutions to this space y 1 and y 2, y 1 plus y 2 cannot be a solution to that one. You have the linear structure here. So, if you have y 1 and y 2 are solution, if you add, you get L of y 1 plus L y 2 is 2 RT, not RT. Okay. So, it does not have the linear structure here, but you will see some affine structure. So, let S tilde be the set of all, so I do not call it a space, be the set of all solutions. Don't we are, when I say that S tilde is the set of all solutions, we are not looking into the initial value problem. Initial value problem has a unique solution. Okay. So, here general solution we are looking at it, be the set of all solutions to the non-homogeneous system. So, let me call it 2 now. So, set of all solutions to 2. So, this see that suppose a particular solution, first you want to understand any solution is called a particular solution, any solution, that is why it is any particular solution, any solution. Let me particular, any solution particular, any function or any function y particular equal to y particular of t which satisfies 3 namely L of y particular is equal to R t is called a particular solution. No constants there, called a particular solution. Okay. So, L y particular solution satisfies this solution, and this is tilde is a set of all is called the a particular solution. There is no 3 here. So, it is not 3, it is 2. Any solution to 2 is called the, there is no 3 here, we are not introduced 3 yet, it is called a particular solution. So, now look at this is an interesting fact. Suppose y, let me to distinguish a homogeneous equation, suppose y equal to y homogeneous is a solution to the homogeneous equation, solution to the homogeneous equation which we already know, homogeneous equation. What does that mean? L of y home is equal to 0, or equivalently y home belongs to S. Let us recall this notation, where S is the set of all solutions to the homogeneous equation, and we know that S has 2 independent solutions only, and the dimension of S is equal to 2. Okay. Then immediately this will give you immediately what about y is equal to y home plus y particular. In other words, what I am trying to do is I am taking a one solution from your homogeneous equation and one any particular solution, then what would be L of y? L of y is equal to L of y home plus y particular. Here is where you use the fact that L is a linear operator. Since L is a linear operator, this is L of y home plus L of y particular. But what is L of y home? L of y home is equal to 0, L of y particular is equal to R of t, that immediately tells you this is nothing but 0 plus R t, that is equal to R. Therefore, y is a, that implies y belongs to S tilde. So, if you start with a solution, any particular solution of your choice, you take any S, the solution from S, add, you get a new solution to your S. So, this immediately tells you that S tilde, if you take S and if you take any particular solution, this is always contained in S tilde. So, what the interesting proposition is that you can immediately prove a proposition in with a one line proof, actually S tilde. So, that is what I said is in a affine form by particular solution. You see, proof is one line, but let me give you a proof. So, you take any S in S tilde. So, you already proved one inclusion, you have to prove the other inclusion. Take any y belongs to S tilde and y particular is given to you, that is what I am saying. So, if you can find one particular solution and then take any solution, so that gives you the complete solution structure. So, any solution to your non-homogeneous equation can be written as the as general solution can be written in this form, and that is what essentially this proposition tells you. That implies, now consider L of y minus y particular again. You consider this, that implies L of y minus L of y particular. But what is L of y? Y is in S tilde. So, L of y is nothing but R, but L of y particular is a particular solution and that is also equal to R and hence is equal to 0. That implies y minus y particular belongs to S tilde S. It is a solution. So, y minus y particular is a solution to your homogeneous equation. Hence, that implies there exists y home in S such that y is equal to y home plus y particular. So, what this tells you is your corollary, which so let me state it another corollary. There is nothing new, I am rewriting the same proposition, but because this is the way probably introduced in the universities and other books. The so this is a theorem, the proposition which I have stated is basically rewriting. Let y1 y2 be two independent solutions to be two independent solutions to your homogeneous equation, solutions of the homogeneous equation Ly equal to 0 and y particular is a particular solution to the non-homogeneous equation, then non-homogeneous equation Ly equal to R, then the general solution of Ly equal to R is given by y is equal to alpha y1 plus beta y2 plus y particular, where alpha beta are constants. You see, so that gives you the complete structure of the solutions to your non-homogeneous equation. So, the problem here is that if you can find two independent solutions to your homogeneous equation and one particular solution, whatever form it is, you can write down your general solution. And if you want to solve your initial value problem, find the general solution, use the two conditions at the initial values, substitute and determine the thing, and that is why the method is there. Again, as you see, finding two independent solutions is the difficult task, and what the reduction order tells you that if you can find one solutions to your homogeneous equation, then using the method of reduction order you can find the second solution. And what we are going to quickly probably describe and a method to find a solution, find a particular solution, even the two if you have two independent solutions to your homogeneous system, that can be used using the method of variation of parameters to determine a particular solution. So, at the end of it, if you look at it in theoretically, you may have difficulty in integrating out the functions, but the end of it the fundamental difficulty is finding one solution to a homogeneous equation. If that is there, you are more or less near the general solution to your non-homogeneous equation as well. So, let me, I have few more minutes in this class. So, let me just introduce the method of variation of parameters, method of variation of parameters, variation of parameters. Yeah. So, we will do that in this class. So, again look how do you, the idea of method of variation of parameters is to determine a particular solution using the two known, if at all, solutions to your homogeneous equation. That is what we want to do it. So, assume, so we are basically assume y1, y2 are two independent solutions, The idea we are going to use is the same as we have used in the reduction order. In the reduction order, if you know one solution y, a second solution cannot be a constant multiple of that equation. So, you varied that constant as a function of t, and fortunately the reduced to the first order equation. Now, we have two solutions y1 and y2. We use these two solutions. If you take a linear combination of y1 and y2 in the form c1 y1 plus c2 y2, that is going to be only a solution to your homogeneous equation. So, if you want a solution to, if you are looking for a solution to your non-homogeneous equation using the linear combination of y1 and y2 with constants on the coefficients is not possible. So, the idea is to vary both c1 and c2 in the coefficients. What I am trying to say is that then for any c1 c2 constants c1 y1 plus c2 y2, then for any constant is also is only a solution, can only be a solution, to Ly equal to 0. You are not, by putting any linear combination of y1 and y2, you are not going to get any solution to the non-homogeneous equation, you will get solutions to only homogeneous equation. So, the idea vary c1 c2 as functions of t, function of t. So, look for a solution, look for a solution y equal to c1 t into y1 t plus c2 t y2 t of the non-homogeneous equation, of the non-homogeneous equation, homogeneous equation. So, what are the things we have? So, we have, so let us consolidate the facts. So, we have Ly1 equal to 0, Ly2 equal to 0, that is a solution to the, and we need, use this thing, we need to find c1 c2 so that Ly is equal to r. So, you need, that is important thing, that is what we are trying to say. Is it possible to find? So, we need to find c1 and c2, two unknown functions satisfying this equation Ly equal to r. So, indeed we need two conditions, and that is what we have to. So, again what I want you to do is that the exercise is to do the computations. Exercise, do the computation. Do the computation. What are the computation you have to do it? With this you find y prime, y double prime and compute L of y. Substitute it in the operator L of y. So, I will write down the expression here. You will get 2 times 2, you have to see where the computation comes here. Let us say 2 into C 1 prime y 1 prime plus C 2 prime y 2 prime, do the computation, plus you get C 1 double prime y 1 plus C 2 double prime y 2, you have a factor here, and you will have P t into C 1 prime y 1 plus C 2 prime y 2, and the q term will get absent because you have y 1 and y 2. Use the fact that L of y 1, you have to use the fact that L of y 1 is equal to 0, L of y 2 equal to 0. Now, our idea is to get 2 equations for C 1 and C 2 solvable. So, the first step is to take, so we are trying to make, and sorry, this is you want L of y equal to 0 and we want this to be RT, that is more important. So, you want that equation to be RT because you want L of y to be the solution to your non-homogeneous equation. So, we are trying to make a simpler thing. First you make this quantity 0. So, these are all imposed whether you can. So, you will have C 1 prime y 1 plus C 2 prime y 2, y 1 and y 2 are given to you. So, you have one equation. So, you have equation 1, let me call this equation 1. Now, look at these expressions. I take, there are 2 terms here, 1 term here. If you do a computation there, if I calculate my d by dt of the here C 1 prime y 1 plus C 2 prime y 1, you see this will give you, if I compute here C 1 double prime y 1, one more term is there, I will write that one. From here I will get C 2 prime y 2, and then from here I get C 1 prime y 1 prime plus C 2 prime y 2 prime. So, if I use this thing, so these are similar terms. So, if I take among the 2 term, if I combine this term with 1 term here, that is nothing but d by dt of this one, but this is already chosen by 0 here. So, this is nothing but 0. So, only term if I choose, this is the advantage, if I choose here I get all this term plus one more term will get cancelled. So, only remaining term will be one more term. So, what I will get is that in that case I will get the C 1 prime y 1 prime plus C 2 prime y 2 prime is equal to RT, and the first equation already I get a C 1 prime y 1 plus C 2 prime y 2 is equal to 0. So, you have 2 equations in 2 unknowns, and this is solvable when this is solvable if this determinant of y 1 y 2 y 1 prime y 2 prime is not equal to 0. But what is this determinant? This is nothing but your Wronskian, if you recall it. This is the Wronskian, you see. Maybe I will what I will do is that I will start from here in the next class, and I will do the as a more or less is done, but I do not want to hurry up, but essentially tells you that you have a Wronskian which will be non-zero because phi 1 and 2 are independent solution, and hence you can solve it for C 1 and C 2, C 1 prime and C 2 prime.